Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. So far in this course, you have learned about the basics of material selection, then we discussed about the classification of composites and cellular materials, followed by the applications and different processing techniques of the cellular materials like metal forms, porous ceramics and polymer forms. In the last few lectures, we discussed about the properties of cellular materials like metal forms and ceramics, porous ceramics in detail. In this lecture, we will discuss about the microstructure and properties of natural cellular solid like wood. You will see in this lecture that wood is a classical example of a natural cellular material, which has both high amount of porosity and also a graded structure, which is very important for structural applications. So, in the last lecture we covered the topics like the electrical properties of forms, acoustic properties of forms, energy absorption properties of forms and also the construction of energy absorption diagrams for cellular materials. The key concepts that we will learn in this lecture are wood as a structural material, then the classification and structure of wood, then the anisotropy of wood and the factors affecting the strength and stiffness of wood. So, the main keywords for this lecture are wood as a structural material, soft wood, hard wood, then cellulose and lignin, anisotropy, moisture content and specific gravity. So, wood, as you know, it is used from very ancient times and it is still very commonly used for many structural applications. There are examples where wood has been used in structural applications from more than 5000 years back. Now, wood is a very attractive material for structural application because wood has many advantageous properties. Like wood, as you will see in this lecture, it has a significantly porous structure, because a significant portion of wood's microstructure is porous and that actually provides wood a very low density and also it possesses good specific strength and stiffness. Furthermore, wood has also good structural anisotropy. That means, as we learned already, there are materials which are isotropic. In those materials, the properties are identical along all directions, and also there are materials which are not isotropic or anisotropic. In these materials, the properties typically vary along different directions. Typical examples, as we have learned already in this course, are fiber reinforced composites. So, you know that if we have a composite like this or we have a material like this, where the reinforcement particles are in the form of particles like this, then you have the properties along all directions, they are identical. However, if the reinforcement is in the shape of a long fiber like something like this, where all the fibers are aligned along the one direction, then you have a strong anisotropy, where the properties along direction 1 will be different from the properties along direction 2. And you will learn today that wood is one such material where we have different properties also along the transverse 3 direction. That means, in wood we have different properties along 3 mutually perpendicular directions, and such materials are also called also known as orthotropic materials. Apart from that, wood also has a graded structure. That means, the structure varies along the length or thickness of the material, and that also provides spatially different properties, which is another big advantage of working with wood. Now, apart from these structural advantages, wood has many other advantages, such as its low cost, because wood is available everywhere and it is also naturally available, and that means the structures which are made of wood, they are often less expensive than other structures from more common structural materials like metals or ceramics, if the same component is available. Also, wood has a very pleasing aesthetics and appearance that also makes wood as a very attractive material. It is very easy to use. That means, it is very easy that wood can be easily cut, shaped and formed into complex shapes, and that is why we see that all around us the components made of wood are very common. Durability, that means if proper care is taken, that means there are situations where wood actually like they swell in monsoon seasons by absorbing moisture, but if proper care can be taken, then wood can last a very long time. And also, as I already mentioned also in the previous in the very beginning of this lecture, wood has extremely good or high specific stiffness and strength. So, as we know, wood has a very low density. There are many woods, we have seen that wood can also float on water, that means wood is even lighter than the water. At the same time, wood has good stiffness and strength along particular directions, and that means that if proper care can be taken and proper design can be made, then wood can have very high specific stiffness and strength. Now, this diagram or this slide actually I discussed at one of the previous lectures, and these basically shows the SB material property map for Young's modulus against density. So, as you already know, this kind of material property charts are very attractive because they actually allow plotting all the materials known in one single plot, and because these plots are log, that means both y axis and x axis are logarithmic in nature. So, we can actually have a very wide range of properties. So, as you can see in this particular plot, we have all the materials Young's modulus against density, and there we see that wood actually covers in this middle portion where we have this kind of pseudo triangular region, which are the natural regions for wood. We also know that in such material property charts we have certain lines which actually denotes the material indices. Like for example, in this chart we have this dotted red line or dashed red line, which actually corresponds to the specific stiffness for bending applications. And we know that all the materials lying on a particular line are equally good for any particular application. The materials which lie above are better for that particular function, and materials which lie below are actually inferior to the materials which lie above for any particular application. So, I can see that this line dotted line has been drawn over here, and it has been drawn through the region where many wood or natural materials actually belong. That means, these are the regions where the natural materials like wood belong, and this line has been drawn through that region. So, what we directly see over here is that now if we just come to this high density region, we can see that this line actually lies above the portion for most of the metals. Like as you can see, the metals they typically lie over here, and this line actually goes over the region where the metals are actually typically located. That means, this automatically shows that for bending beam application, wood is a more attractive material than most of the structural metals we know, like steels or even aluminum and those alloys. So, that actually renders wood very attractive for such applications like bending beam. Like for example, in many western countries where cold winter months are there, I have shown you in the previous slides that there are often the beams are made of wood because they provide excellent structural stability. Now, wood can be typically classified as either softwood and hardwood. So, as you can see in this slide, so softwood they are typically characterized by needle shaped leaves. That means, the conifer trees, as you can see in the hilly areas, those trees are basically, or the wood from those plants or trees, they are called the softwood. And another feature of these woods are that the trees that have softwood, they typically have they are typically evergreen in nature. That means, they do not shed their leaves in the winter months. In contrast, we also have the hardwoods, and the hardwoods, as is being shown on the below picture, the hardwoods are those which have typically broad leaves. That means, most of the trees which you see around us in the tropical countries are typically the hardwood, and they are typically deciduous in nature. That means, they shed their leaves during the winter months. The structure of the wood, again it varies from plant to plant or tree to tree, but typically the structure of the wood is made up of the fundamental unit is called the cell, and the cell of the wood is typically made up of hollow tubular cells. That means, you can see in the next slide. So, typical examples of the structure of the wood cell, the cylindrical cells are being seen over here, and where, as you can see, that these cells have a preferred orientation. That means, these cells are typically oriented along the length of the trunk. That means, normally you will see that the cells, if you cut the cross section of a wood, you will typically see that the cells are typically like in the horizontal in the vertical direction, and there are only few cells which are actually oriented along the horizontal direction. Now, what is the basic composition of the wood? Wood typically consists of 3 to 4 basic materials. The major components of wood are basically cellulose and lignin. So, among that, cellulose, which is around half of the wood's constituent, this is the main load bearing element of the wood, and it also provides the wood with its typical strength and stiffness, which we actually look for in the structural applications. And then we have the lignin, which is around 20 to 30%, and this lignin actually acts as the glue that holds the cellulose fibers together. That means, as we have already seen, in composite materials we have the fiber and the reinforcement, fiber and the matrix. So, you know, in a composite material the fiber is the main load bearing element or the component, and the matrix is typically soft, which actually bonds the fibers together and actually transfers the load from the matrix to the fiber through the interface. The similar kind of concept can also be thought in case of wood, where actually the lignin is actually acting as the matrix, which is actually transferring the load to the cellulose, which is the main load bearing component, and also lignin actually provides the wood its stability because it holds the cellulose fibers together. Then we have around 30% of hemicellulose, and also there are some minor components like resins, oil, tannins and so on. Now, if we typically consider that the wood is mainly consisting of the main structural elements, that means the cellulose and the lignin, then it typically have a density of around 1.54. That means, typically if wood does not have, I mean if wood is made up of completely bulk, that means there is no porosity in the wood, then wood would be heavier than water, because together cellulose and lignin, they have density higher than the density of water. But as I already mentioned, wood is basically made up of the hollow cells. That means, these cells that you see over here, these cells are mostly hollow, and because of these hollow cells, these porous cells in the wood, that actually provides wood the low density, and that is why wood, which is density between 0.3 to 0.75, this can actually float in the water. And these hollow cells of the wood, it also provides wood with a very good mechanical properties, because as we know that if a cell has this I mean if the loading direction is something like this, like we have the hollow cylindrical cells like this, and then the load is applied along this direction, either tension or typically compression, then in that case actually there will be strong anisotropy. That means, along the direction of the cells, that means along the vertical direction, along the trunk direction, we have very good compressive strength, whereas if we compress along this direction, that means if the cells are compressed along the transverse direction, along the horizontal direction, if the trunk is like this, then actually wood has very poor mechanical properties. So, I repeat, wood has excellent strength and stiffness along the long axis of the cells, which is typically also along the trunk direction, and along the transverse direction, which is the thickness direction of the cells, wood typically possess very low strength, and this is because the cells are all hollow cells. Now, because in these hollow cells, the transverse properties of the wood are very poor. So, typical examples are being shown over here. So, as you can see over here, so if we compress along this direction, then wood will typically show excellent mechanical properties, but at the same time if the compression is along this direction, then wood possess very poor mechanical properties. Also, this is about the compressive strength. There is also the presence of shear strength. That means, if we shear along this, that means if it is sheared along this direction, then again the properties will depend actually on the strength of the lignin, because this lignin, as we already mentioned, this is acting as the glue which is joining, or which is kind of joining the individual cellulose fibers to each other. That means the strength of the lignin actually controls whether the properties or the shear properties, when we are shearing like this, whether the shear properties are actually higher or poorer. If the lignin has a high strength, then the shear properties will be shear strength will be higher, and vice versa. But all in all, if we just classify the strength of the wood along different directions and different kinds of strength, we will typically see that the compressive strength along the longitudinal direction is the highest, and then we have the shear strength, and then this transverse strength, that means the crushing strength along this direction, and the transverse direction of the wood, this is the lowest among all the strengths that we can think of in woody materials. At the same time, because wood possesses these hollow cells, and now if these cells are put under bending, that means if we can assume that this is a typical wood which is mostly hollow, because this is mostly hollow, this is the beam of wood, and now we are actually subjecting this part to bending. Then because of this hollow internal, or the hollow portion inside the whole trunk, wood has excellent bending stiffness. So again, wood possesses excellent compressive strength along the cell direction, along the trunk direction, and also wood has excellent bending strength because of the hollow internals. Now, this effect of the loading direction on the properties of the wood is being shown over here. So, as you can see over here, this slide basically shows the x axis and y axis. So, either it shows the specific modulus, which is nothing but the E over rho, and also the strength, and this is basically shown against the microfibril angle or off axis angle along the x axis. So, basically what do I mean by that? That means you can see the schematics being shown over here. That means if we can assume that, that means if we take a wood like this, so this is basically the situation for your angle equal to, if we take the angle as alpha, this angle equal to 0 degree, and now, so this is now this is our loading direction, and now if the loading direction, and now this is actually the main axis of the trunk. That means if the loading direction, the compression direction is along the trunk axis, then we have alpha equal to 0 degree. Now, suppose the loading direction is now changing, that means the loading direction now is no more like this, it is now increasing like this. For example, so if this angle now alpha 1, then this is alpha 2, this is alpha 3, and going to alpha 4 90 degree, right. So, if we keep on increasing keep on tilting the wood, that means if we assume that the wood trunk is remaining constant, and then we are tilting the loading direction, or other way around, we are keeping on the loading direction is remaining constant and the wood is being continuously tilted, right. So, the effect of this tilt or the change in the angle on the strength and stiffness is being shown in this slide. And as you can see, in all cases, as we increase the angle, that means as the orientation of the wood is changed from its vertical orientation to more off axis orientation or to more tilt orientation, then actually the properties will continuously decrease. So, this, as I already mentioned, wood has highest properties when it is loaded along the cell direction, that is along the trunk direction. However, as we move more towards the off axis orientation and at 90 degree we reach the transverse orientation, then the properties of the wood will vary significantly and will be much lower. Now, another important point I already mentioned at the beginning is that wood is not isotropic. So, I already mentioned that isotropic materials are like when we work with typical metals and they are not having any texture, like in the cast condition, when there is, for example, with the small dendrites or whatever like that, then we expect that the metals or those alloys to be isotropic. That means the properties should be same along all directions. Typical example, if I draw a structure like this. So, for example, this is my one direction, this is my two direction, and this is my three direction, and in case of a typical isotropic material, there is no preferred orientation and you have all properties same along all direction. So, these materials, like typical, as I mentioned, as most of the metals and their alloys and also particle reinforced composites, they are the typical examples of isotropic materials, and this is a big advantage of that, because when we work with those materials, we need not worry about the working direction. I mean, in whatever direction we apply the load, the material behavior will remain the same. But you already learned that a more complex situation actually arises in case of those materials like the fiber reinforced material. So, if I just draw it like this, and a fiber reinforced material, typically the fibers, like if this is our one direction, this is our two direction, this is our three direction, and all the fibers are oriented along the one direction, then actually in this case we actually have different properties along 1, 2 and 3. In this particular case, the property, that means if E is the property like the Young's modulus, E1 will be much higher than E2, which will be equal to E3. So, that means in this particular case we can see that if all the fibers are along the one direction, then we have very good properties along the one direction, and we have similar but lower properties along directions 2 and 3, and these typical examples are called transversely isotropic. So, transverse isotropic with respect to one direction. Now, this is definitely more complicated than this isotropic case, because now we have to worry about the orientation. That means, when we load such fiber reinforced composites, we have to worry that all the load is being put along the one direction, because if it is not done like that, then we have poor properties along 2 and 3, which will actually reduce the applicability of the material. Now, there can be even more complicated situation where actually typically wood belongs to those kind of situation, where even the properties along 2 and 3 directions are not identical. That means, typically you can see in this diagram over here, we have actually 3 different main axes. So, the first axis is again the axis along which the trunk axis, this is the axis along which all the elongated cells are oriented. So, as you can see over here, all the elongated cells are oriented like this. So, we have this is called the longitudinal axis or the cell axis, right. But now we have a situation in case of wood, if you make a section cut in the wood, then you do not have identical properties along the tangential axis and also along the radial axis. So, basically you will see that in such kind of a material, the properties are actually varying along 3 mutually perpendicular directions. That means, if you take as this point as your origin, and then through this point you draw 3 mutually perpendicular directions inside the material, then the properties will vary along all 3 directions, and such kind of materials are called actually orthotropic. So, such kind of materials with mutually different properties along 3 mutually perpendicular directions are known as the orthotropic materials. So, again typical examples of such a material and the properties along different directions are being shown over here. So, what is being shown? So, this is a work by Hasegawa et al. And so, what they did, they took a piece of wood like and then after proper treatment, what they did, they tried to measure the sound velocity along the 3 mutually perpendicular directions. So, that can be very easily done using an ultrasonic sensor. That means, you can put 2 sensors on opposite sides, and then along different directions you can try to measure the sound velocity. So, in this case, as you can see, the velocities are being measured along longitudinal direction, along the tangential direction, and also in the radial direction. and the values are being shown over here. So, as you can see the VL, which is the value along the L or longitudinal direction, which is much higher. So, now as we know that the Young's modulus of a material is actually proportional to rho times V square, that means where rho is the density and V is actually the sound velocity inside the material. So, from this relation, as we already expect, we can see that along the L direction, that means along the directions along which the cells are oriented, along that direction we have the highest sound velocity, which basically renders the material to have the highest stiffness along the L direction, whereas along the two other directions, that means along directions radial and tangential direction, we have lower sound velocity, and that will automatically transfer into lower moduli along these two directions. However, the velocities along VR and VT, they are lower than VL, but they are not identical. That means we can, this follows typically VL is more than both VR, which is not equal to VT, and correspondingly we have that the properties or the stiffness of the wood will vary along the three orthogonal directions, and wood is an orthotropic material by nature. Now, there are different factors which affect the strength and stiffness of wood. Among them, we will discuss some of the factors over here. The most important factors are, as you can see over here, moisture content, gravity, then loading direction, and also some other properties like the species, like which kind of wood is being loaded, the size and shape of the component, because typically it is observed that the bigger the component, the lower is the strength, and also the nature, size and location of the defect. That means the more the presence of defects, the as expected the strength will be lower. Now, as we know, moisture content plays a very important role, because we all know that depending upon the type of the wood is actually very much able to absorb the moisture. We all know that in monsoon seasons in our homes we have seen that many wooden furnitures or even the doors, they do not try to close, right, because wood tends to absorb the moisture, and by doing that its dimension actually increases, it tends to swell, and by doing that actually it is actually susceptible to warping or some kind of damage in light. So, basically the moisture content of the wood is defined as the amount of moisture it has absorbed, and this is typically found out by finding the wet difference between a dry wood, which is typically obtained by taking a wood and drying it in oven for a certain amount of time to vaporize all the moisture, and then the wet difference between the original wood with the moisture and the dry wood after the moisture has been dried off, and this difference is used as the moisture content. Now, typically if we plot the strength and stiffness of the wood with the moisture content, so basically as the moisture content increases, the strength and stiffness typically decreases, as is being shown over here. So, here you see that along the y axis we have the compressive yield strength along different directions, and again you can see that the sigma L, which is the strength along the cell direction, is much higher than the sigma R and sigma T, the tangential and the radial directions. But in all directions, as the moisture content increases, so initially the drop in the strength is drastic. That means, as you can see, after around 10 to 15%, there is a very sharp drop in the strength and stiffness, but at higher moisture content the values typically level off, and this point around 15 to 20%, around this point starting from which the strength and stiffness becomes almost constant. This is the critical moisture content for that particular wood variety. Also, the specific gravity of the wood also has a strong effect on the properties. So, specific gravity, as we already learned, so wood is inherently porous material. Now, and because of the presence of the pores, we already know that the pores, they play a big role in controlling the mechanical properties of the cellular materials. The more the amount of pores in a material, there will be the lower will be the mechanical properties. At the same time, there are materials, because of the presence of the pores, the density also decreases, and as a result we may have more or higher specific properties. That means, the presence of pores. So, as the amount of pores increases, both the strength decreases and the specific and the density also decreases. So, basically it is actually it is not the strength as such, the important thing is the specific property, which is the sigma over rho, that means if sigma over rho is actually can be maximized, then actually the pores can actually be beneficial in actually giving better specific properties. Now, as we know that wood has significant amount of porosity, and now if the specific if the density of the wood increases, that basically means that the amount of cellulose and lignin in the wood is also increasing. That means, the higher the density of the wood, the more is the amount of cellulose, and as we know that cellulose is the main load bearing component of the wood, and correspondingly the strength of the wood and stiffness of the wood will also increase with increasing density. So, typically we see that the properties of the wood follow this kind of a relation over the specific gravity. So, where F is any property which can be bending strength, which can be compressive strength, which can be stiffness and so on. Sg is the specific gravity, and here K and N are basically constants, and we can see in this table that for many properties like the bending strength, the modulus of rupture, the compressive strength and so on, for many properties actually these typically follow this relation with different values for the constants K and N. Also, one more important property of wood is that it is a time dependent behavior, because many a times when we work with the woods, the wooden components are loaded, I mean they are put under load, and the load is maintained over a very long time, and under such conditions actually wood is susceptible to time dependent deformation called creep. That means, as we all know from our knowledge of metallurgy or material science, that creep is actually a behavior where if the load is remained constant, then the deformation that takes place over time, this is called the creep deformation. And typically, as in many materials we already know, the creep curve of wood also shows 4 different regions. So, as you can see over here, the moment the wood is loaded, typically you have an instantaneous deformation which is mostly elastic in nature, but then as the load is remained constant over time, you initially have a reduction in the rate of deformation. That means, initially the rate of deformation decreases over time till it reaches kind of a plateau region, and this initial region between points A and B, this is called the primary creep. In the primary creep region, at a constant load with increasing time, the rate of deformation of the strain rate continuously decreases. Then in the region B to C, which is more or less a linear region, kind of a constant, the deflection remains more or less constant. That means, the deflection rate becomes more or less constant or 0, and this point where this deformation remains constant, this is called the secondary creep, and this is the this is also the minimum creep rate, and this point is the most important for any creep deformation. And finally, starting from point C to D, that means after certain amount of time, then the deformation actually kind of accelerates, and we have a very increasing rate of deformation until the final failure, and this point, this region where we have this increased rate of deformation is called the tertiary creep or the final creep region, which culminates into the failure of the material at point D. Now, this creep curve or the shape of the creep curve typically depends upon the amount of stress, that means how much stress has been applied. So, again in this case sigma 4 is actually more than sigma 3, then sigma 2 and sigma 1. That means, as we keep on increasing the stress, that means the load applied on the wood as it is continuously increased. So, initially we see that we have the instantaneous deformation over here, but then depending upon how much load is being applied, we might not have the tertiary point or tertiary creep at all or the failure at all. That means, if the load is very low, then this stress plateau or this of the secondary creep or the minimum creep rate, that might actually continue for a very long time. But if the applied load is very high, then we see that we attain the secondary and tertiary stage and the failure at a very less amount of time. So, that means again the amount of load that is being applied is again very important for wood deformation. So, to summarize, in this lecture we learnt about the basic mechanics and properties of wood, which is a very important structural material available in nature in large amounts, and we learned that wood is actually a material which combines many of the aspects of cellular materials we discussed in this class, such as the presence of a large amount of porosity, the presence of strong anisotropy, and also wood can also have strong gradient structure, and which we will learn in the next lecture that this gradient structure is actually one very important aspect which these hybrid materials can actually offer to provide properties not achievable with the monolithic materials. The structure of woods, as we learned, typically consists of cellulose, which is the main load bearing content of the component of the wood, and also lignin, whose main function is to glue the cellulose fibers, and apart from that we can also have hemicellulose and some minor constituents. Again, the cellulose materials and the structure of wood is typically consists of the hollow tubular cells, where the cells are mostly oriented along the trunk axis, along the length of the wood, and that actually provides wood very good mechanical properties along the length of the cells. That means, again, if this is the trunk of the wood, then the cells are mostly like this, the hollow cells, and these will provide very good mechanical properties along the one direction, that means along the trunk direction, whereas the properties transverse to the cells, that means along this horizontal direction, we typically have very poor properties, which also depend upon the properties of the lignin, which acts as the bonding between the cellulose fibers. So, the main references for this lecture are listed over here, and in the next lecture we will discuss about FGCMs or functionally graded composite materials. Their main definition and properties will be discussed in the next lecture. Thank you very much.